Our senior design project for spring 2017 was to create a persistence of vision display. This display had to display custom material, in our case specified text by an end user, as well as a generic demo mode that displays Clemson and Go Tigers in a scrolling fashion. In order to accomplish this, our team came up with a cohesive design to integrate both physical and electrical paraphernalia. As can be observed here, our display utilizes a wooden frame covered with a plexiglass shield to house a DC motor fitted with an aluminum blade. This blade holds our microcontroller, the Tiva TM4C123G, along with LEDs, shift registers, a Hall effect sensor, batteries, wires, and resistors soldered onto a protoboard. In order to provide an output display, programming is done in Code Composer in a C environment to control the outputs of 16 linearly placed LEDs. Our display features green light for the output, compactly and cleanly placed electrical components, adjustable motor speed control, portability, and stability. Persistence of vision is the illusion created by our eyes to perceive constant images as well as animation based on quickly changing frames of images, as shown in the visual demonstration here. In our case, we had to control the illumination of the LEDs to blink on and off based on our desired letter. Pictured here is a Tiva, which controlled shift registers to drive the blinking of LEDs using three main signals: the serial data, the shift clock signal, and the latch clock signal. Voltage and ground from the board also powered the shift registers. Our preliminary design sought to use an individually addressable RGB LED strip, which only needed one data line of voltage source and ground. However, after the strip continued to hinder rather than help us, we went back to the idea of a linear array of RGB LEDs to output our display. Thus, we had to understand the capabilities of the Tiva's GPIO pins and how to use shift registers to control LEDs. Pictured here are the shift registers, which allow all 16 LEDs to be controlled with only 3 pins on the Tiva. These are 8-bit serial in, parallel out shift registers that allow data to be sent to the shift registers, which is latched, shifted, and then output to the LEDs at prescribed frequencies to display the desired characters. In order to control the timing of our display, we also had to research the function of a unipolar latching Hall effect sensor that could send feedback to the Tiva when the display moved across a specific point. As shown in this demo, there's a voltage signal sent by the sensor shown in the LED turning on when the magnetic field changes. A magnet is placed at an origin point on the wooden frame to drive the timing of the Hall effect sensor, which is placed at the end of the spinning blade so that it can detect the changing magnetic polarity. Here, the Tiva can be seen mounted on one end of the blade and wires going out to control the power of the LEDs through shift registers. This is the protoboard in which there are 6 shift registers, 16 RGB LEDs, resistors, and wires to connect voltages, signals, and ground. The LEDs are placed as close to each other as possible to obtain a clearer output display. On the bottom of the board, one can observe the soldered connections, as well as more signal wires in the Hall effect sensor circuitry. This PWM DC motor control offers a simple knob to control the voltage going to our DC motor, thus controlling the speed at which our project is rotating. And with all of these devices hooked up properly, here is our finished product. Here is a demonstration of our project, first turning on the Tiva to receive onboard power from a 5-volt USB power bank, then turning on the switch to the DC motor, and turning the PWM control knob to increase the speed of rotation. Here we see the default output of scrolling text. We can also decrease the speed of rotation while still being able to observe the output. Lastly, we can observe how increasing the speed makes a more cohesive image while adding a little bit of noise on the physical build. Then we can turn up the knob to stop the blade from rotating. And as we do this, we can see the LEDs blinking on and off. And lastly, we can turn the switch off to safely disconnect the motor from its battery, and turning off the Tiva will stop the LEDs. Our next demonstration shows our ability to show custom text. Our self-made GUI allows an end user to type whatever string they would like, limited to 15 characters, and informs that the string was sent. As the video shows, this text is stably outputted onto the display.
you.